Now that we have discussed measuring distance, area, and volume, in this lesson we will focus on measuring weight. There are a lot of similarities in this lesson to the previous lessons. First of all, for measuring weight, we again have two systems, metric and the English system. Notice that for the metric system, it's almost exactly the same as with distances and meters. The only difference here is the metric system is based off of the gram instead of the meter, but everything else is similar where you have a single gram. To increase in size, you multiply it by factors of 10, and to decrease in size, you divide by factors of 10. That makes converting in the metric system very simple. Basically, again, we're just going to move around a decimal point, either to the left or to the right. And for the English system, we'll have to use dimensional analysis when doing conversions. Let's first focus on the units that are in the English system. We can weigh things using ounces, pounds, and tons, and the connections between them are 16 ounces is equal to 1 pound, and then 2,000 pounds is equal to 1 ton. Because of these conversions, ounces, they are used to measure things that are light, for example, maybe a pen or a slice of bread. At the other end, tons, they're used to measure things that are very heavy, perhaps like a car. Pounds is going to be used for everything in between things that are light and things that are very heavy, so maybe something like the weight of a kitchen table. Now, if we compare that to the metric system, the starting point is a gram, and I believe 1 gram is about the weight of a paperclip. So you can use that as a reference to how heavy a single gram is. Now, if you have 10 grams, or the equivalent 10 paper clips, that's what we call a decagram. 10 times more would be a hectogram, and then 1,000 grams, or the weight of 1,000 paper clips, is what we call 1 kilogram. So for this reason, kilograms would be used to weigh things that are heavier than a gram, like maybe, I don't know, a pile of bricks or something like that. Going in the other direction, if you start at a gram and divide it by 10, you'd get a decigram. If you divide by 10 again to get 1/100th, that is a centigram. And if you divide by 10 one more, we get 1 milligram. That is a 1,000th of a gram. For this reason, milligrams would be used to weigh things that are extremely light, like perhaps the amount of medication that was in some type of tablet. It might be something like 5 milligrams or 50 milligrams. But what about things that are really heavy, like a car, for example? Well, that's what this conversion factor is for up here. So we have an idea of what it means to be 1 kilogram. Well, if you have 1,000 of these kilograms, that's what we call 1 metric ton. So similar to tons in the English system, we need a unit that can measure things that are very heavy, and that's what this is used for here. Now that we've discussed these different units and their conversion factors, in example 1, let's start with the metric system. I'd like to convert 3.2 kilograms into grams. I will first use dimensional analysis, but as we'll see, ultimately we're just moving around a decimal point. So we have 3.2 kilograms, and according to this thing here, 1 kilogram is equal to 1,000 grams. Dimensional analysis says you have to set up a fraction with kilograms in the denominator and grams in the numerator. For every 1 kilogram, there is 1,000 grams. Again, I'll set it up so the first thing here is a fraction. We can cancel the kilograms, and all that's left over is 3.2 times 1,000 with our unit of grams. The nice thing about multiplying by 1,000, what it will do is take this decimal point and move it 1, 2, 3 places to the right. That's going to be 3,200 grams, and that will be the answer. But the reason for using the metric system is so you don't have to do this process here. So a faster approach would be, we're starting with a larger unit and dropping down to a smaller one. For things to remain equal or balanced, that means this number at the end must become bigger. A faster approach to this problem is to say, okay, well, we have 3.2, and I'll add some zeros, kilograms. I look up here and say, okay, we're starting here, and we're going 1, 2, 3 places down. That means we're going to move this decimal point 3 places to the right. So it should go over a total of 1, 2, 3 places. And really, the answer would be 3200, and that is now in grams. So you don't need to use dimensional analysis to solve this. You can, but if you're in the metric system, it's all about moving the decimal point. In this case, it went to the right because the number had to become bigger. So let's try this again now with converting 4.1 milligrams, these things, to decagrams, which is up here. Let's take the approach of moving a decimal point. So we're starting with 4.1 milligrams. So we're here and we go 1, 2, 3, 4 places. We are moving the decimal point 4 times. But the question is, which way does it move? To the right or to the left? We're going up to a larger unit. For things to remain balanced, the number must become smaller. That means the decimal point is moving 4 places to the left. So that's 1, 2, 3, 4, which will put a 0 here, 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 and then one before we get to this 0. So the answer here is 0.00041, and this is decagrams, abbreviated DAG. So in this way, metric is nice. Don't need to do dimensional analysis. We can simply move around a decimal point to go from one unit to another. Before moving on and doing more conversions, I want to address one thing, and that is weight versus mass. Sometimes these terms are used interchangeably, but there is a difference between them. When we say the mass of an object, we mean how much matter is contained within that object. And the more mass an object has, the more it will weigh. But weight is different because this is determined by the gravitational pull of the Earth. So weight is really a force due to gravity. So the greater the mass, the greater the weight, and the smaller the mass, the smaller the weight. Now you've probably heard that on the moon, you weigh less than you do on Earth, and that's because the gravitational pull of the moon is smaller than that of the Earth. But the difference here is your mass on Earth and your mass on the moon, that does not change. You can't change the amount of matter that an object has, but the weight can change depending on where you are located. So that being said, let's continue with converting back and forth between different units of weight. In example 2, I'd like to try 2 things. 1, let's convert within the English system, therefore we'll have to use dimensional analysis. But also, we should be able to convert between the English system and the metric system, so we'll try that too. Let's first convert 56 ounces into pounds. Both ounces and pounds are in the English system, so we have 56 ounces. And to convert this, we'd like to cancel ounces and be left with pounds. What we need to know is, what is the conversion factor between pounds and ounces within the English system? For every 1 pound, there is 16 ounces. I'll write the first value as a fraction, and by setting it up this way, we cancel ounces. We have 56 times 1 times pounds, and the denominator is just the number 16. So when we multiply across, we get 56. We have pounds, and this is all divided by 16. To simplify this, I want to divide 16 into 56. That means the denominator will be 1. We won't have to write it. And then I'll put pounds at the end as our final unit. I'm going to do this in my calculator. 56 divided by 16 is 3.5 or 3.5 pounds. The second part of this example says to convert 660 kilograms into pounds. So here we have our starting point of 660 kilograms. And in order to convert this, we are going between metric and the English system, so we have to use dimensional analysis. I'll set up a fraction. The denominator must be kilograms, and the numerator must be pounds. So what's the connection between the two? Up here I have a conversion factor that is stated. You don't have to memorize this. It says that 1 pound is approximately 0.45 grams? That's not right. That should be 0.45 kilograms. With that correction, we can set things up perfectly. For every 1 pound, there is 0.45 kilograms. Now we're good to go. We can set up the first one as a fraction, and we can cancel the kilograms. In the denominator, we're doing 1 times 0.45, and there are no units, so we get just 0.45. In the numerator, we have 660 times 1 times pounds. We get 660 pounds divided by 0.45. In a calculator, I'll divide this into this, and I'll have pounds left over. Okay, I have a decimal, so I'm going to round it to the nearest tenth, but the number I get is 1,466.7, and this is in pounds. So 660 kilograms is approximately 1,466.7 pounds. There is another commonly used conversion factor for going from kilograms and pounds that maybe you're familiar with. 2.2 pounds is approximately equal to 1 kilogram. Like this could be used too. What would it look like to solve this problem using this conversion factor instead? I say we try it out. You'd start with 660 kilograms, and you'd multiply this by, well, again, you want to cancel kilograms, so it goes in the denominator, and pounds is in the numerator. But this time we're saying for every 1 kilogram, there's roughly 2.2 pounds. I kind of like using this one better. Here, when you multiply across, you can first cancel the kilograms. The denominator is completely equal to 1, so we don't have to write it. This should just be 660 times 2.2, and we'll have pounds left over. Okay, 660 times 2.2 is, this is different. I get 1,400. That's good, but then it says 52 pounds. What gives? That looks significantly different. And the reason is these conversion factors are approximate. If you'd like these answers to be more accurate, you'd have to include more decimal points in your conversion factors. For example, this one, 1 pound is roughly 0.45 kilograms. I didn't know the exact number. I had to look it up. It's more like 1 pound is equal to 0.4535927 kilograms. Like that's more accurate. So instead of using this number, you could use this number to get a more accurate answer over here. For this one, again, I had to look that one up too. A more accurate conversion factor is if you have 1 kilogram, that's equal to 2.2, but then 0.4622618 pounds. So these are more accurate. These are rough approximations because we're using fewer decimals, and that was the reason for the difference between these two answers. When solving the homework, use the provided conversion factor just to make sure that you get the estimate that the system is looking for. The other topic in this lesson is measuring temperature. And so I'll start with a question. What is a good room temperature? I don't know if you thought of an actual number, but what do you think of something like 68 degrees? Does that sound good? Or maybe you prefer something like 20 degrees. I'm sure you already know where I'm going with this, but the degrees really depends on which unit you are referring to. And the two common ones are degrees Fahrenheit and degrees Celsius. So on the left here, we're talking about 68 degrees Fahrenheit. And on the right, we're talking about 20 degrees Celsius. And it turns out that 68 degrees with the units of Fahrenheit is equal to 20 degrees with the units of Celsius. Now, what's the difference between these two units of measurement for temperature? And how do we know these are actually equal to each other? Is there a formula that connects them? Let's describe those things. First, The way these two units are similar is they assign numbers to the freezing point of water and the boiling point of water. So I'll say the freezing point of water. So that'll get some number assigned to it. And then there'll be a larger number that is assigned to the boiling point of water. And room temperature should be somewhere in between those numbers. The way these are different is they assign different numbers to these things here. Let's start with Fahrenheit. Some number has to be assigned to the freezing point of water. It definitely should be something less than 68. And that number that is assigned is 32, and then I'll put degrees Fahrenheit. Likewise, we have to assign a number to the boiling point of water, and that number should be greater than 68. In fact, that number is 212 degrees Fahrenheit. So over here, it was basically pick some numbers that are nice to work with, and we're good to go. Now, how does that compare to Celsius? What's the choice for the freezing point of water? Okay, so over here, this is 0. 0 degrees Celsius is when water freezes, and that seems like an obvious choice. What about the boiling point of water in Celsius? What would be maybe a good choice for a number? It turns out it's 100. 100 degrees Celsius. With these numbers established, we've now created a scale for temperature. 2 different ones, in fact. So the next question is, well, with these 2 different scales, how can you convert back and forth between them? There are formulas for this, and I'll state them now. Here's one for converting from Celsius to Fahrenheit. F, which will stand for Fahrenheit, is equal to 9/5 times Celsius plus 32. And the one going from Fahrenheit to Celsius in the other direction is Celsius is equal to 5/9 times Fahrenheit minus 32. Let's see if these formulas work by testing to see if these two numbers are equal. If I put 20 degrees Celsius here, will it simplify to give me 68 degrees Fahrenheit? Let's see what happens. So for Fahrenheit, that's equal to 9/5 times 20 plus 32. So 9/5 times 20. Okay, 9/5 times 20. Okay, this is 36 plus 32, and that in fact does equal 68, and that's degrees Fahrenheit. Now this formula should go in the other direction. If you put 68 in place of Fahrenheit and simplify this, it should give you the corresponding Celsius degree. So if we try that out, Celsius is equal to 5/9. That's 68 minus 32. Now 68 minus 32 is 36. So C is equal to 5/9 times 36. And 5/9 times 36 is in fact equal to 20. So you can put any Celsius degree in here and convert it to Fahrenheit. And over here, you can put any Fahrenheit degree and convert it to Celsius. So let's try using these formulas again in an example on the next slide. In example 3, I like to convert these temperatures from either Fahrenheit to Celsius or Celsius into Fahrenheit, and we'll be using these formulas here to do so. We will round to the nearest tenth as needed. Let's start with 10 degrees Fahrenheit. I want to convert this to Celsius. That must mean I use this formula over here. I put 10 in place of Fahrenheit, and when I simplify all this, the result should be Celsius. So, for 10 degrees Fahrenheit, if I go to the formula, C is equal to 5/9. I'll put 10 in place of F and subtract 32. Let's see, 10 minus 32, we're going to get a negative number here. So we're going to get negative 22. This is 5/9 times negative 22. A negative, if there's only one and you're multiplying together, means the entire result is going to be negative. It'll be negative 5/9 times 22. And 5/9 times 22 If I round to 1 decimal, the 10th place, that is Celsius is equal to negative 12.2. And again, that's degrees Celsius. So 10 degrees Fahrenheit is negative 12.2 degrees Celsius. Notice that this is freezing. This is below the freezing point of water, but we still have a positive number. Yet over here, it's a negative number. One benefit of using the Fahrenheit scale is that when temperatures drop below the freezing point of water, you'll still have numbers that are not negative, and that's not the case for degrees Celsius. Okay, let's try 31 degrees Celsius. So we'll have to convert this to Fahrenheit, which means I'm going to use this formula here. So for that one, 31 degrees Celsius, I'll go to the formula. Fahrenheit is equal to 9/5. Okay, that's 31 for Celsius, and then we add 32. All right, if we simplify this, 9/5 times 31 is, we get 55.8. And we are adding 32 to that. And so when we add 32, we get F is equal to 87.8, and that's degrees Fahrenheit. And for the last one, negative 40 degrees Fahrenheit, which is pretty cold. So since we're converting to Celsius, I'm going to use this one here. I'll put negative 40 here and simplify it to solve for C. Let's see what we get. Okay, so C is equal to 5/9. Then we have negative 40 minus 32. So Celsius is equal to 5/9. A negative then minus 32. It still is negative, negative 72. And since one of the numbers is negative and we're multiplying, the entire answer is going to be negative. So C is going to be equal to negative 5/9 times 72. Now, what is 5/9 times 72? 9 goes into 72 8 times. 8 times 5 is 40. And so that's equal to negative 40, and that is degrees Celsius. So there we go. If you have negative 40 degrees Fahrenheit, that is equal to negative 40 degrees Celsius, which that seems a little strange, right? I mean, these are different units of measurement, but we actually get the same number. This is the only time where this happens. The temperature at which degrees Fahrenheit is equal to degrees Celsius, and the number is actually the same. Why did this happen? It seems a bit strange. The reason is the scale is different. In Celsius, you're only going from freezing to boiling 100 units. Now, in Fahrenheit, because you're going from 32 to 212, you're going up by 180 units. So these don't increase at the same rate. And that means they actually meet at some point, and in fact, exactly once. And this is the temperature where that happens. Just in case you're curious, why is this formula true? How do we know that this works? This is actually related to a linear equation. Y is equal to mx plus b. This is the equation of a line. Notice that this formula has the exact same format of this thing. It's a variable equals some number times another variable plus another number. Essentially, this is the equation of a line. If you want to find the equation of a line, you have to have 2 points to draw that line through. So I'm going to come up with 2 points. Those 2 points are 0, 32 and 100, 212. So here, this is Celsius and this is Celsius. Here, this is Fahrenheit and this is Fahrenheit. And with our points, we're connecting the freezing point of water and the boiling point of water. I want to find the line that goes between these 2 points. And that means you have to find the slope and also the y-intercept. Well, what's the formula for slope? It is change in y over change in x. On my points, I can call this x1 and I can call this x2. My y values, I can call this y1 and this one y2. Using the formula for slope, I'm going to do y2 minus y1 divided by x2 minus x1. That is 212 minus 32, all divided by 100 minus 0. If we simplify this thing, that is 180 over 100, and that's really 18 over 10 if you cancel the zeros. And if you cancel a factor of 2, hey, you get 9/5. That's the slope of the line, which matches up with this. So in terms of trying to find the equation of the line that goes through these 2 points that connects Fahrenheit to Celsius, we have half of the question. Y is equal to the slope, which we just found, which is 9/5, x plus, well, we still have to solve for b, which is the y-intercept of the line. To solve for b, you can use either of these points that you would like. This is the easier of the two to use because one of the coordinates is 0. Essentially, if you want to find b, you can put 0 in place of the x, you can put 32 in place of the y, and the only thing that you won't know is b. So let's see what happens when we do that. So just to reiterate, I am putting 0 here, and then I'm going to put 32, the y value, here. And when I do that, my equation becomes 32 is equal to 9/5 times 0 plus b. Anything times 0 is 0. This whole thing is 0. That's 32 is equal to 0 plus b, and I don't need to write that 0. I get 32, and that's what b is equal to. I found the slope. I found the y-intercept. If I fill all of those in on the line, that's y is equal to 9/5 x plus 32. And the y values are what we're calling Fahrenheit. I can call that F. The x values is what we're calling Celsius. I can call this C. When I swap those two things, I get F is equal to 9/5 C plus 32. So if you've ever gone through the process of finding the equation of a line that goes between 2 points, here's an application for it. This process actually derives the formula that we were using in the previous example. If you remember, there was a second formula. There was one that wasn't F is equal to something in terms of C. It was written the other way. C is equal to something in terms of F. Where does that thing come from? You can solve for that by taking this equation and solving it for C. I'm going to try that too, just to see what it looks like. I'll do that here. F is equal to 9/5 C plus 32. If you're looking to solve for C, you could first subtract 32 to the other side of the equation. On the left, we'll have F minus 32 is equal to 9/5 times C. So I move this to the other side. These two things are still equal. If you want to get C by itself, you don't want this 9/5 here. What can you do to both sides of the equation to cancel 9/5? You can multiply by the reciprocal, and the reciprocal is 5/9. You have to do that to both sides of the equation. On the right, 5's cancel, the 9's cancel, and you're left with just C. I'll put that here. We have, on the left, 5/9 times F minus 32 is equal to C. It's written backwards, but that was the other formula that I stated. So I wanted to outline this just because it's a neat application for finding the formula for the equation of a line. So these formulas are derived from somewhere.